Hi, my name is Jesada. We are from Group 1 and we are going to present about 1,3-butadiene.
1,3-butadiene is a chemical derived from petroleum processing. The majority of 1,3-butadiene production is dedicated to the synthesis of artificial rubber. The French chemists successfully extracted butadiene through the pyrolysis of Maillard alcohol. The identification of this hydrocarbon as butadiene occurred in 1886, following its isolation by Henry from his byproduct of petroleum pyrolysis. There are three methods contribute to butadiene production. First, steam cracking of paraffinic hydrocarbons. In this process, butadiene is generated as a co-product during ethylene synthesis. The retrieved butadiene undergoes a purification process with carbon-carbon and carbon-hydrogen bonds breaking at approximately 800 degrees and 33 kPa pressure for less than 1 second. The second is catalytic dehydrogenation of N-butane. The dehydrogenation of N-butane to produce 1,3-butadiene involves the hydrocatadiene, a well-established one-step process in operation. This adiabatic process occurs in packed bed reactors at temperatures ranging from 600 to 680 degrees under a partial vacuum of 0.1 to 0.4 bar using a catalyst comprising aluminium and chromium oxide. The third one is oxidative dehydrogenation of N-butene. Oxidative dehydrogenation of N-butene involves the removal of two hydrogen atoms by adding oxygen, converting N-butene to butadiene. This process offers advantages over non-oxidative methods by completely converting two butenes and producing substantial amounts of 1,3-butadiene at lower temperatures. In typical processes condition, there is 1:1 ratio of inlet composition, operating pressure of 0.5 bar. Temperature is set as 130 degree to 280 degree. There is 90% typical reactor conversion and 85% selectivity. Rennet liquor is act as catalyst. This table shows some physical properties of 1,3-butadiene, such as melting point, boiling point, vapor pressure, and density.
Next is synthesis route. First, hydrogenation of 3-hydroxybutanol give 1,3-butanediol. The hydrogen gas undergoes adsorption onto the catalyst surface. Subsequently, hydrogen dissociates into two active hydrogen atoms while situated on the catalyst. The 3-hydroxybutanol featuring an aldehyde compound that adsorbs onto the catalyst surface. The metal catalyst facilitates hydrogen atom transfer during this phase. Then the aldehyde group experience reductions leading to the formation of an alcohol group. Finally, the product 1,3-butanediol is dissolved from the catalyst surface. Second, dehydration of 1,3-butanediol give 1,3-butadiene. The process involves the dehydration of 1,3-butanediol to produce 1,3-butadiene through the elimination of water molecules. The reaction types is characterized by the elimination of water molecules from the diol structure. The adsorption of 1,3-butadiene onto the catalyst surface is the initial step in the reaction. Water elimination follows, causing the removal of adjacent hydroxyl group from the diol structure. Finally, the elimination process results in the formation of double bond between the carbon atoms that were previously connected by the removed hydroxyl groups. Next is the reactor types. We chose packed bed reactor because it well matched for catalytic reaction and enable effective contact between catalyst and reactants, facilitating chemical transformation. Packed bed reactors also excel in providing efficient temperature control and heat transfer. PBR crucial for handling exothermic processes in 1,3-butadiene production, dissipating heat effectively. Next is hotspot prevention. Helps prevent issues like hotspots that could compromise the reaction integrity. Next is mass transfer, where PBR facilitates mass transfer process, ensuring efficient delivery of reactants to the catalyst and product extraction. And lastly is the surface area. Substantial surface area is in PBR enhanced mass transfer rates, contributing to overall reaction efficiency.
This is our AutoCAD design. We have three components, which are body, top and bottom. And as you can see here, these are the 2D wireframe and also realistic design from the top and also from view. And for the dimension, as for body, we use radius 1.5 meter and the height is 35 meter. And the radius for bottom and top is also 1.5 meter. And The total volume of our design is 261.45 meter cube, and the porous part we use radius 0.3 meter.
Next is the multiple reaction. In this project, we have two reactions. For the first reaction, if the rate law is negative R1A equal to K1CaCb. For the reaction 2, the rate law is negative R2C equal to K2Cc. And for the overall reaction, the rate law is negative R3A equal to K3CaCb. Therefore, from the rate law equations for the reaction 1, 2, and overall, we can get the relative rate equations for each reaction shown in table above, while the table below shows the net rate of each component for component A, B, C, D, and E.
Next, for the reaction kinetic, actually we don't find exact reaction with us, but we found a similar one. For the reference one, we can use the fifth reaction from the table, where the value of K is 2.76 plus minus 1 times with 10 power of 5 exponent of 1 over RT. Next, for the second reference, we found all the values, and we found that the last value of R1 is equal to 49.21 exponent negative 162.67 over RT times with the pressure of C4H8O2 alpha divided by 1 plus 511.06 Pa pressure of H2O power of 0.32. And for the R2, the one that is equal to 7.93 exponent negative 170.99 divided by RT times with the pressure of C4H10O2 alpha and times pressure of C3H4O beta divided by 1 plus 24.46 pressure of H2O times exponent power of 0.57. For the third reference, it's already given the value of the K reference 1 and 2, which are 7.45 times with 10 power of negative 4, and also the K reference 2, which is 4.41 times with 10 power of negative 4. After considering all the reference, we chose reference 3 because it's more similar with our reaction, and we use K reference 1 and K reference 2 for the calculation.
Okay, next for the calculation part, we need to make an assumption. First, all reactions involved are elementary reactions. Next, the reaction is in isothermal and isobaric condition, where isothermal T naught equal to T, isobaric P naught equal to P. 3. Since K3 is overall reaction mixture of K1 and K2, then K3 equal to K1. By using overall reactions, A plus B equal to D plus 2E. By using overall reaction, we can subtract stoichiometry table and table for net rate, where negative at A nets equal K1 CaCb. To calculate volume and catalyst weight, by using basis equal 100 kg over day and FT we get 0.15135 mole over second. By using temperature and pressure from the literature review, we can get Ca naught equal 34.58 mole over m cube. And then we can get the initial molar flow rate and volumetric flow rate. By using all the data, we can calculate the volume of the PVR and assume the process will run for 4 hours a day, and V equal 237.61 meter cube. By using the volume, and we can get the D equal 5.6 m and length equal 10 m. To calculate weight of catalyst, by using rate law, design equation, and stoichiometry, and then we combine it together and we can get W equal 10.9 kilogram. To calculate selectivity and yield of each product, by using Ca naught, then we can get concentration of each species, and then based on K1 and K2 from literature review, we can get selectivity equal 0.5, yield of the desired product equal 0.2233, and yield of undesired product equal 0.4466. So for the MATLAB stimulation, we need to input concentration of A, concentration of B, and volumetric flow rate. And then the MATLAB will auto calculate and it will print out the weight of the catalyst, selectivity, yield, product, and yield, undesired product. This is coding for plotting the graph yield versus concentration. So this is our product, weight, selectivity, yield of desired product, yield of undesired product, and graph for yield versus concentration. That's all from us. Thank you.